Go ahead and start the recording. And if you've just joined, like Ellie's cat has just joined, be thinking about what movies you would recommend, what space movies you would recommend that others should watch during the winter break. So we'll be starting with that question here in just a minute. Today's topic is going to be space and how that relates to engineering. Okay, welcome everyone. It's 11 o'clock, so we're going to go ahead and start. I want to, so let me share my screen. So today we're going to talk about space, and this should be a lot of fun, but it's also, it's pretty educational. So what we're going to be doing is we're going to be tying those two things together, both learning about space from a very kind of engineering standpoint, but also understanding what some of the fun aspects of this. So I thought I'd start with this set of pictures. I've got 4 pictures here. 3 of them are actually places and things that you could do, and 3 of them are actually out of space movies also. The point is that most space movies are made on Earth. And so if you see the picture on the lower left, that I took in a desert in Jordan, a place called Wadi Rum, and it's exactly the same place as where they filmed The Martian, which is above it. If you look at the Spherio that is there in the lower right, those are actually made by a company in Boulder. And the way that that thing moves is all done with gyroscopes on the inside, and that's just taken in some desert with some spaceship wreckage in the background. So only the one in the upper left, which is from the movie Gravity, would actually be difficult to do without actually going into orbit. And we'll be talking about going into space. Last time we shared what movies you'd seen, and that was kind of from my list of movies. But now in the chat, if you could write what movies you would recommend that other students should watch during the winter break, because they're just cool movies about space, and they can be TV series as well. So just go ahead and write in the chat what movies you would recommend. And I think what I will do, so yeah, go ahead and after class, I'll take that list and I'll work out how I can share it with everybody in the notes from this module, because I think that's pretty cool. And certainly I plan during the winter break to be watching some of your recommended movies as well, because I think there's a lot that one can learn from these kinds of films. And what we're going to be doing is looking at some of these from kind of a critical eye of how does the actual engineering on this stuff work. Okay, so feel free to add more in the chat if you've got other ones. Let me tell you a little bit about what we're going to do. So as part of the homework assignment, you had some calculations to do. Those calculations help understand what it takes to get to space. That's where we're going to start. They'll also, as we talk about all of that, I can tie that into manned versus unmanned space exploration and some of the things that have been going on in that regard and some of the limitations. Then you were also asked to identify interesting space missions, and we'll have some breakout groups where you'll be sharing those space missions. And then finally, I want to talk about the fact that actually there's a lot of jobs in this whole space world as well, and how that relates to some of the different engineering disciplines. So let's get started. So this is the calculations that you needed to make. There are 51 students in the class, and 42 of you attempted these calculations, and 27 of you got the calculations correct. So I want to make sure all of you understand this. This is a good lesson in making sure that you are very careful about units. But the conclusion from this is also very important in terms of understanding what does it take to get to space. So it involves kinetic energy and it involves potential energy. Let's do the kinetic energy calculation first. You have, we were moving 100 kilograms to space. The equation is 1/2 mv squared. And the units for joules are kilograms meters squared per second squared. So you were given the orbital velocity as kilometers, and kilometers is 1,000 meters. So you had to do the conversion from 7.8 kilometers to 7,800 meters per second. You had to square that, multiply by 100, and you would end up with almost exactly 3 billion joules, which can also be called 3,000 million joules or 3,000 megajoules. And for reference, I've also divided that by the 100 kilograms to give us a number of megajoules per kilogram, because we'll be using that a little bit later. So now let's compare that to the potential energy, which is the mass times the acceleration due to gravity times the height difference. When you do that calculation, again, the 400 kilometers needs to be converted to 400,000 meters, and you end up with 400 megajoules, or 400 million kilogram meters squared per second squared. So the point of that is that it is kinetic energy, i.e. velocity energy, which is greater than potential energy when you want to get to the International Space Station. And it takes about 7.5 times the amount of kinetic energy than potential energy. And that's really important to recognize, that most of space travel is limited by the amount of energy it takes to get to the velocity in order to get to anywhere and to do anything. So that's where that's really worth sharing. Remember that space starts at 100 kilometers. And so that to get to just 100 kilometers, which is the edge of space, takes 1/4 the amount of potential energy. So then it would just take 1 megajoule per kilogram if you had 100% efficiency. And so people who offer you a trip into space, that's much easier to do than a trip into orbit. And let me illustrate that another way. The first rocket to ever go into space was a German V2 in 1944. It took another 13 years to develop a rocket that was powerful enough to put an object into orbit, which was Sputnik in 1957. That was done by the Russians. And by 1961, they worked out how to put enough of a mass into space that an astronaut could actually go, and that was Yuri Gagarin in 1961. That was all the Germans and the Russians. Until 1962, the Americans did not have a rocket powerful enough to accomplish this, to actually put a man into space. And the Russians, the reason that Yuri Gagarin was the first man to go into space is he was short and he was very lightweight as well. So mass is also very important in terms of the energy that's required. So that's critical to understand, but we're going to now look at, we were talking about 100% efficiency. So now let's look and see how efficient are the rocket engines in being able to do this. So what we're doing, it's another energy equation. In this case, we're taking chemical energy in the form of the fuel and oxidizer, and we're turning it into kinetic and potential energy. So let's look at that calculation. We know that 100% efficiency is 34 megajoules per kilogram of payload. That's what we did in the earlier calculation. We're going to look at two rockets, the Russian Soyuz rocket and the Falcon SpaceX 9, the Falcon 9 full thrust. And here is how many kilograms of fuel plus oxidizer that each of those have when they're on the launch pad ready to launch. The amount of energy that is in that particular combination of kerosene and liquid oxygen is 9.856 megajoules per kilogram. The amount of kilograms of mass that each of these two rockets can put into low Earth orbit is what you see there. So the Falcon can put about twice as much as the Soyuz. And so then your calculation to understand how many megajoules of fuel and oxidizer are used is you take A, which is the number of kilograms of fuel and oxidizer, which is in kilograms. You multiply that by B, which is the megajoules of energy per kilogram. And then you divide that by the number of kilograms that you're putting into space. And you can see that we get those two numbers that you see there. So the Soyuz rocket, 330 divided into 34 is approximately 10% efficient. And the Falcon 9, which is a much more recent rocket, is 13% efficient. So that shows you that this stuff is super inefficient. Now, why is that the case? Well, in previous years, we spent more time on space, so I would actually have students understand more before we had this discussion. So I asked students this question, and I want to share with you two answers that I got from different students. One is if the cost to launch a kilogram into space was less than $1, people could just launch so many things into space carelessly every day, which would result in releasing lots of harmful chemicals into our atmosphere. The price has to be really high because launching so many things into space is really bad for the environment and would result in lots of money spent to fix those problems. The mass has to be big so that it sets a limit on what objects people can launch, resulting in less objects being launched into space. So that's a very interesting idea, but it assumes that governments set the laws for how things work. As it turns out, it's actually a physical limitation. And I want to talk about that physical limitation in the words that another student used to describe it. The main reason that you cannot convert 100% of the energy of kerosene into kinetic energy is because the fuel has significant mass and that fuel is burned continuously instead of instantaneously. As a result, when you burn 1 kilogram of fuel to lift 1 kilogram of payload, you need to accelerate the mass of the fuel as well. So when you light the engines of this rocket, you're actually accelerating all of the mass at liftoff. This additional mass increases the inertia and reduces the effective delta V, which is the change in velocity of your rocket. So you need to add more fuel to reach the desired 7.8 kilometers per second of delta V needed. Overall, this produces a delta V function that is logarithmic. So that second description is actually how it works. And I've created an optional tutorial, which you will see when you go to the module for this particular class, that goes through that rocket equation. And you're encouraged to look at that, but you're not required to know or understand that for this class. I will give you a very, very brief overview of some of the things that are relevant in terms of thinking about engineering. So it's a complex subject, and there's lots of complex subjects that you're going to be learning. When you need to learn a complex subject, my recommendation is take it in small steps and learn it from multiple sources, because then it will be much easier to try to understand this stuff, right? You just got to kind of pace yourself. Another useful thing is to visualize how it works. So if we were doing this class face-to-face and we were not wearing masks, I would be handing you balloons now, and you would inflate the balloons, release them, because that's basically the same way that a rocket engine works. The equations that are used is the physical laws conservation of momentum. Visually, what that looks like is if you have a single mass made up of M1 and M2 traveling at one velocity, as you see on the left, and you push part of that mass out the back end, as you're seeing being done there in the mass on the right, it will accelerate M1 relative to M2. So basically that's what rocket engines do, which is the same as what balloons do. And the equation that governs that is the conservation of momentum, which says that M1 plus M2 times V1, which is the diagram on the left, has to be the same as M1 V2 plus M2 V3. So if we create a difference in these two velocities, we can get V2 to increase. And it is that concept that is used. In the tutorial, I go through in detail the derivation of all of the equations that are used to do this, and I use the 7-step problem-solving method to do it. The final equation that you end up with is that the change in velocity of the rocket is the factors that you see there, and it's based on some key assumptions in terms of how much of the structure of the rocket is fuel and how much of it is the actual containers for the fuel, if you will, and how much of the rocket is the payload and how much is the part of the rocket that's eventually removed, and then how efficient is the engine, which is measured by something called specific impulse. And to give you a little bit more detail on that equation so you have a bit of a feel for it, so the change in velocity, which needs to be 7.8 kilometers per second to get into orbit, is based on this concept of specific impulse. Specific impulse depends upon the kind of a rocket that you use. And most rockets that we are currently using to go, or all rockets that we currently use to get to space, are either solid fuel rockets or liquid fuel rockets. And those have some very specific physical limitations in terms of how high you can get that specific impulse. If you multiply that by the acceleration due to gravity, you get numbers in meters per second of somewhere around 2,500 for solid fuel rockets and 3,000 for liquid fuel rockets. And ion thrusters, which you might have heard about in some of the movies you watch, actually produce a lot more specific impulse, but they have a problem, and the problem is in the right-hand column there. They produce very small amounts of thrust. So where a solid rocket produces in the meganewtons of thrust, a ion thruster produces on the order of millinewtons, micronewtons, I mean millinewtons, sorry. And the difference between millinewtons and micronewtons is 1 billion times, 10 to the 9th. So ion thrusters don't have enough thrust to actually counter gravity and allow a rocket to actually move, but they are what's used in spacecraft when they are finally in space, because there sometimes you need to accelerate something and you have years in which to accelerate it, and then ion thrusters do that very efficiently. So when you look at that equation and you plug in typical values for the structure and the amount of payload, what you end up with is that the natural log of 1 plus the structure ratio over the payload ratio plus the structure ratio comes out to about 1.9. When you multiply that 1.9 by the values of how good these rockets are, you end up with a delta V of about 5.7 kilometers per second, which is not enough to get into orbit, which is why all the rockets to leave the Earth require multiple stages. So they basically throw away part of the structure in order to lighten the load in order to get further. So that's basically, it takes all this kind of stuff to get a rocket up. So there's a lot of hard science regarding getting to space. It takes a lot of kinetic energy. It takes some potential energy as well, but that is less important. The current rocket engines are really inefficient, and throwing away your rocket after 5 minutes of use is really wasteful from a financial standpoint. So it's kind of like every time you drive to the grocery store, you have to buy a new car. So that's basically how we now get to space. But the US, it was a very rich country, and using that technology in the 60s and 70s, the US accomplished a bunch of very cool stuff. We got the first humans on moon, and return them. That was in 1969. We had the first safe landing on Mars. That was the Viking mission. And we've had a number of them since that time. And in 1977, we also launched a rocket called Voyager, which by 2013, after 36 years, actually left the solar system. So those are very, very cool missions, but they were done basically using that technology. So now the new revolution in getting to space is making improvements in the way we do it. And there's three kinds of improvements that are worth mentioning, and one that is probably still quite a ways in the future. So you can see that we talked about the specific impulse of various rockets. We are making improvements. So the latest SpaceX rockets are likely to be above a specific impulse of 300. But you can see that those improvements are really incremental, and the percentage of the spacecraft that's actual structure, we're also trying to get that down by using even lighter materials in order to do things. But one of the very cool things that SpaceX wasn't the first company to do it, but the first company to really do this very reliably for big rockets, is we're now able to land the first stage of a rocket and reuse it, which significantly reduces the cost because we're not throwing away our engines every time we use them. Now, there's more stuff that is being investigated, and this is where things get cool, okay? Because there are other alternative technologies for getting to space. The one that is already getting to be commercialized is, instead of using rocket engines, use jet engines. Get the launch vehicle up to as high of an altitude as possible and as high of a velocity as possible before you launch the rest of the way. So for about $100,000 in this decade, you'll be able to go to space. You won't be able to go to orbit. You'll go just above 100 kilometers. So it's just the potential energy part alone. And it will be in vehicles like this that get reused, and they basically get launched from jet aircraft. Next technology that's being looked at is if you could accelerate everything on Earth, it would be much better. So the idea is, if you think about a bullet is basically accelerated in a rifle. The equivalent is something known as a railgun, and you may want to study that a little bit further. And the problem is the railgun needs to be so long in order to accelerate at a rate that humans can actually withstand, but that is another technique and technology that can be used, and you'll see more things and people experimenting with that also. The third technology sounds really, really exotic, and that is the old beam me up Scotty technology. And we won't actually be doing that with people because that's too complicated. But if instead of having to put things into space, we could use materials that are already in space, so we could mine things from asteroids or from the moon and get fuel in that way, that would allow us to get a lot more things into space, because launching from the moon takes a lot less energy because the forces of gravity are a lot less. So bringing 3D printers up and then 3D printing using materials that are already there is a little bit like beam me up Scotty, and you will start seeing people working on that as well. Another technology, pretty exotic, but there's already practical ways that we do something similar, is known as a space elevator. So if we have a very strong rope or cable and we attach it to a counterweight, and the counterweight is up high enough, then that it circulates the Earth at the same velocity as the Earth rotates, then we could basically have this elevator that could go up and down the cable, and we could go into space that way. So there are people who are investigating that. It's a materials problem, having a material that is strong enough to actually make the cable. But we're already doing some things similar to that once we're in orbit, because if you've ever heard of the concept of gravity assist, where we use some of the momentum of something that is already in space in order to impart some of that momentum to a spacecraft. That's kind of the same as this concept of the space elevator. The one concept that doesn't work is trying to build a really tall tower. The tower would have to be so phenomenally tall that there's just no materials that we can ever imagine that I think could get there. But concepts A, B, C, and D do have some feasibility, and so there are things that are actually going on to do that. But the biggest way we are improving our ability to go to space is we're sending less mass. So by making spacecraft smaller, we can send them up cheaper. And these days it costs $100,000 to orbit 1 kilogram. And so it's starting to get to the point where individuals can afford to send up their own satellite or to send up their own thing, as long as you can make it ultra lightweight. So that's where a lot of this stuff is going in terms of the world of engineering, and looking at space in terms of tools of exploring the tools of science. So now what I'd like to do is have each of you share your investigations in this. So as part of the homework, you had to find a space mission that you thought was cool. So I'm now going to break you into groups of 3 or 4. And I will assign you to a group, and this will take me a second because I forgot to do a couple of things. So let me do those things first. And then you will share your ideas and with others, and then you turn this in as part of your homework. So got to do 2 things here, and then we'll be ready to go. Okay, so I'm going to put you in groups of about 3, 2 to 3. And there you go. Okay, welcome back. All right, welcome back, everyone. So what we want to do next is I want to share a little bit more about these also. Hopefully you learned something from your breakout groups, and what we want to do is build a little bit more on that also, because there's a couple of missions that I think are worth sharing as well. And we're going to do an iClicker question that's related to that. So if you can go ahead and get your iClickers ready, I'll share with you what I'd like to get your inputs on. And that is another aspect of going to space and the science that we are supporting with all of this engineering. So I want to ask you the question, is there life beyond the Earth? All right, that's extraterrestrial life. And let me know which of these you think best fits what you know. That yes, and we've already found enough evidence to prove it. Yes, and we'll find enough evidence to prove it during the next 10 years, or yes, there is life beyond Earth, but we won't find enough evidence to prove, we'll find enough evidence to prove it later this century, or it will take even longer than this century to find enough evidence, but yes, you do think that there is life beyond the Earth. Or the final category is no, you don't think that there's life beyond the Earth. So just let me know which of those categories you fit into, and then we'll go see what your results are, and then we'll talk about some of the things that are going on in that world as well. Because I think that's certainly a very cool aspect also. All right, so that should be enough time. Let's go look at those results. Oh. So 15% of you, all of you think that there is life beyond Earth. That's pretty interesting in itself. And that most of you think it will be found sometime later this century, or well, what's interesting is it's kind of about a 50-50. So let's let me share some things with you in terms of that world, because I started learning more about that world when I was in Antarctica. Because when I was in Antarctica, they were also finding evidence of life in places there that they had never found before. And so one of the big questions is, what do you define as life? So what has already been found is the ingredients and the right kind of habitability, i.e. Combination of pressures and temperatures and chemicals and everything else in other places beyond Earth. So that has been found in a number of places in our own solar system, and they are finding an increasing number of what appear to be habitable planets in other solar systems as well. So that tells us one thing. The other thing is that meteorites that have landed on Earth, they have found amino acids. And amino acids are the building blocks for proteins. Proteins are the building blocks for DNA. DNA is found in viruses, and organisms also have all of those ingredients as well. What has not been found yet is DNA sequences. So viruses and similar, no one has been able to find them outside of the Earth, but there are a number of missions that are starting to look at this also. And nobody has found bacteria or similar, which are very definitely life. But what needs to be said is that there are all kinds of places on Earth that were thought to be not habitable, like the South Pole, like hydrothermal vents, tens of thousands of feet below the ocean at phenomenal pressures with no sunlight or anything, where there are bacteria that live in those kinds of places also, under the ground, far below the ground. So it is quite possible that some of those things can be found. So now tying into that map of time, we've gone through this particular history, but now let's do a little bit of future looking. There are two kinds of things that will be very difficult to do in space missions. One of them is having humans go to Mars, especially if we want them to return, because the amount of energy to lift them off of Mars and to have them return, the amount of time that it takes because of the velocities involved, that is a very daunting task. The other thing that will be very difficult to do is the first object to actually go to another solar system. And the reason for that is those are such phenomenally huge distances. And again, velocity is very difficult to obtain at the kinds of velocities that this would take. And so that's not something that you could expect to see happening in your lifetime. It might be possible to have the first humans on Mars, but will they actually be returned? That's a bigger question. But there are two things that are very cool that are planned for this next decade, and I want to talk about both of those. One is to bring samples back from Mars, which that mission will launch in this decade, but it'll take until 2032 for us to bring it back. And another one, which will also launch in this decade, is to land on one of the moons of Saturn. And that's scheduled to launch in 2026. So let me talk about those two. This is the first one, which is to sample and return samples from Mars. So the first part of that mission has already started. It started in August, which is the Mars 2020 rover, Perseverance. It will go to the surface of Mars and it will fill canisters with samples. It will then, it will leave those canisters in its path as it has gone and done something. Then there will be another mission, which is NASA is launching several years later, which will go to Mars and collect all of those samples and bring them to a launch site. And then NASA, in combination with the European Space Agency, will launch a third rocket. That third rocket will, and that's actually that second rocket, what it will also do is it will take those samples that it has collected and it will launch them into Mars orbit. The third rocket, which is this joint venture with NASA and the European Space Agency, will take that sample after it's orbiting Mars, pick it up, and bring it to Earth. And so by 2034, we will have samples from Mars that will actually have gotten to Earth. And that is a big accomplishment. And it also shows how much more difficult it would be to actually send astronauts to Mars and bring them back. Now, the other mission that I want to talk about is truly exotic, but also feasible given current technology. And that is they're going to basically launch the equivalent of a helicopter, send it to one of the moons of Saturn, a moon called Titan that has an atmosphere on it. And they know enough about that atmosphere and its density and the gravity that they have worked out that they could design a kind of one of these rotor drones that could then fly across the surface of that particular other world. And so they'll also do, they'll take samples, they won't return them to Earth, but they will take all kinds of measurements, and they think that that particular planet or that particular moon of that planet may actually have life on it or have a lot of that biology. So very cool stuff that's going on. So now let's talk about the final topic, which is how could you in your career be involved in some of that? So first off, I want to identify that you might not even need to leave the state of Colorado, because there are a number of companies here in Colorado that are working on all kinds of things related to space. The picture that you see on the right is United Launch Alliance. That is actually that Mars mission that I talked about, which I also talked about at the beginning of the semester. And United Launch Alliance is in Southwest Metro Denver, and they build those kinds of rockets. So all the things that we've been talking about in terms of rockets, that's their world. The second one is Ball Aerospace. Ball Aerospace, some of you had the James Webb Telescope as one of your very cool missions. Ball Aerospace in Boulder is building the James Webb Telescope, a lot of the components for it. They build a lot of large satellites that do all kinds of very interesting things. They are a large organization that does this. and they are in the large satellite business. There are now many other smaller companies that are building these very small satellites as well, and many of those are in Colorado. And then the third company that you see there is Sierra Nevada Corporation. They're in Louisville, Colorado. They are building the Dream Chaser. When Scott Tibbetts came to class, his company became part of Sierra Nevada. So they also build all of these actuators that get used in all of these other space missions. And what you see there on the Dream Chaser, you see that thing that's on the back end? That's basically a big trash bin as well. So, so the front part actually returns to Earth and the back part burns up in the atmosphere. But let's look at that a little bit further and talk about how this relates to various different engineering disciplines, depending upon what engineering discipline you go into and what kinds of careers are involved. Civil engineers build structures, and the structural engineering part of civil engineering was involved in a lot of the structure that's being used in the International Space Station. So those kinds of calculations, if you have a civil engineering degree, you could go into the structure of rockets, you could go into the structure of things that get built in space. Mechanical engineers, the engines, the materials, the actuators, and the rovers like these Mars rovers are things that mechanical engineers are involved in that are related to space. Computer engineers, very important, and that has to do with the control systems on these kinds of aircraft. The SpaceX is competing with Boeing to bring astronauts to the International Space Station. Boeing launched a rocket in the middle of this year to demonstrate that they could go to the International Space Station. The problem they had was they had flaws in the computer control systems. So this is a very critical area. I actually know the person who does this. It leads the team that does this for Sierra Nevada Corporation. It's a very complex subject, needs lots of really talented computer engineers. Environmental engineers. If you bring people up into space, you have to keep that environment habitable. You have to control the various kinds of chemicals that are produced. That's very much in the realm of what environmental engineers do. Chemical and biological engineers. When we start looking at how we're going to make things in space, the same things that chemical and biological engineers are learning, a lot of those manufacturing processes will end up getting used, and that's how they fit. Electrical engineering and physics are involved in trying to make these more advanced engines like these ion thrusters. And electrical engineers are needed everywhere in almost every project that's space related. So that's everything that I have to share with you in terms of what we want to talk about on space. It looks like we're just about out of time for class anyway. You've got a relatively short homework assignment that's due tomorrow night. And then we've got Friday's class, which will be the last class. And then that'll be followed by an assignment that you will do as your final assignment. So we're almost there, and we're almost into your winter break. So start thinking about some of those space movies and some of the things that you want to do during your winter break. So that's it for today. Feel free to hang on if you've got any questions, and we'll see you on Friday.